in Australia. So this is in one of the snowfields earlier this morning. It's got nothing to do with gasification though. So this time we have been getting quite low temperature all the time, and quite a bit of snow as well. So good for the snow business. So I thought we'll change the tempo a bit, go to cold, and before going back to hot again. Okay. So this is the other type of gasifier, which is also quite mainstream, and it was developed from the FCC technology. In FCC, if you can, those who do not know, they work at very, very high velocities. FCC, fluid catalytic crackers. So it's a technology developed by Kellogg Brown and Root, KBR, and eventually was commercialized at 550 megawatt scale by Southern Company Services. Works around the same temperature range as fluidized bed, but biggest difference is it's an extremely fast fluidized bed. So again, it has got two stages. One is in the lower stage, where we have air or oxygen enriched air, and then steam as well. But coal is fed here. So this is predominantly a pyrolysis zone, and here onwards combustion zone, and whatever volatiles are formed here, because volatiles form at very low, within a very short few seconds, as you have noticed before. So their purpose is to capture all the volatiles unaffected. So that's why they are not injecting anything in this region. So everything is down below in here. This is also called the mixing zone. This is the riser zone, because it's a two-stage. That's how they differentiate. And between this and that, the volume reduction is such that you get very high velocity. So here you get more time, there you get high velocity, and that high velocity also facilitates the particle separation, cyclonic separation of the solids, and then eventually it goes to the primary gas cooler and particulate control device, whatever it is. So their solids velocity is 10 meters per second, but no other gasifier you will see operating at that kind of velocity at all. This is the only one. So there is a plant, there's a lot of work that was done in North Dakota, at Wilsonville, and I was associated part of the way back in 2004, 2005, that period. And then subsequently there was a larger plant built at Wilsonville in Alabama, and based on the testing from there, the plant was built with DOE support at Kemper County in Mississippi. So this is the back at 2013 when it was at its peak. That's where they published these computer generated images to show the location and exactly how the plant configuration will look like. And because it's a pressurized one, and because it's a dry feed one, that's why they have had a fluidized bed dryer, and the fluidized bed dryer was going to be the one that we discussed about on day one, and the Great River Energy, the dry fining carbon, hot air fluidized, and hot water cooled. And they had plans, not just for IGCC production, but also had plans with the sulfuric acid and ammonia production, because if you generate hydrogen from the gasifier, you can also get nitrogen from the separation plant if you want to. Then you can generate the ammonia through the conventional processes. And then sulfuric acid processes as well. I believe the facility was kept in order to use the sulfur in the gas, in the coal, and therefore in the gas. So transport reactor was also a mainstream. At present, my understanding is that after commissioning and after few years of run, they have stalled it because of cost blow up, tremendous cost blow up. And then the other one is the Rocketdyne gasifier. This was promoted by Pratt & Whitney, the company which makes and sells rocket engines and the aircraft engines as well. It's an extremely high pressure but very compact. So they did all sorts of experimental work at pilot scale at GTI, Gas Technology Institute in Chicago, bit at CanMet in Canada, and but it has almost 30-40 years of history behind the development of it. The main advantage that they promoted or claimed was that everything will be much smaller because of high pressure. And there were a couple of, because they had the experience of combustion of fine particles in a compact gasifier like that, or in a hot environment. But the biggest issue is the development work that they wanted to have, want to identify to be carried out as the dry solids feeding pump, because there was no information available whatsoever on the ability to feed fine particles at a very high pressure. And that they had done a fair bit of work on the gasifier itself, but then a pilot plant to build or demonstration plant to build was going to be the proof. My understanding is that at present there is no such development work going on, but of course the information are still in the hands of the proponents. So that's the major gasifier types that I wanted to bring to your attention. So the other advantages that they said that it will be a single stage, be oxygen blown, and up to 70 bar pressure, and flame temperature can reach very, very high. And they can tolerate solidified slag layer. Metal wall is kept cool to 550 degrees or 40 degrees Celsius, same as the steam generation temperatures. Coal feeding is pulverized, but that was to be demonstrated by 2015, but we don't hear about that anymore. And they have tested some of these fuels. The left side is the sub-bituminous, bituminous bordering onto that range. Then petroleum coke from another location, and then also sub-bituminous coal. And but it's the ability to handle apparently the high sulfur coals was touted as very big plus of that technology. So I had shown this to you in the first presentation or second presentation, so I'm not going into you anymore. There's predominantly the major suppliers of gasifier are the fast 4, but this one is rapidly increasing. The Chinese one, their capacity in the total production. So the major coal-based IGCC projects. The first one was Bugenam in Netherlands, the shale type. Then the Puerto Llano in Spain. There's the plain flow type, but it's a variant of shale. Wabash Energy, which is USA. ConocoPhillips, now called E-Gas. Tampa in Florida is a GE type. And then Nakoso in Japan, MHI type. I haven't listed any of the Chinese ones because information is not easy to obtain. But there were other projects that were supposed to have come on stream. The Green Gen in China supposed to have been commissioned by 2018. The first stage was going to be 250, and then second stage we were going to have 400 megawatt, but we don't hear from it anymore. Edwardsport is 618 megawatt. It was supposed to have been come a long time ago, but it has been shelved. Magnum IGCC together with CCS, 400 megawatt, again hold. Mississippi Power, the Kemper County project, based on lignite, 580 megawatt. The installed cost of per kilowatt was 5,500. To put in perspective, the cost of supercritical PF is about $2,800 to $3,000 per kilowatt. So per kilowatt. So when you say 580 megawatt or 400 megawatt, it's a huge cost, capital cost, capex, that you're talking about. Therefore, unless you are making other kinds of products, valuable products that you can sell and then make money, gasification for power generation only is not going to fly. That's the fact. How the cost can come down is a different issue. The more of these plants are built, more experience learned, fine-tuned them accordingly. That's how it is. That was the history of pulverized coal-fired power generation plants as well over the decades and close to century. But this is the current status, if I may say so. So what are the R&D needs as we move to the next phase of gasification lecture? One is obviously knowing the reactivity of the coal, because it's such a slow process, gasification, compared to combustion. That is very, very important. And knowing the coal reactivity and through testing is extremely important. And then for the design of the gasifier, you really need to know the reaction rate equation. Not always, I mean the reaction rate equation. Of course, it will be based on the fundamental principles, but then you have to generate an equation that can be amenable to use in modeling, so that you can actually use it for modeling purposes. And models are used to do what? Models are used to do scaling up. So therefore you need to have a very good understanding of the kinetic expressions appropriate for that coal, appropriate for the condition. And then the other thing that I haven't actually at all mentioned, but we'll do that when we talk about the gas cleanup, is the trace element partitioning. So there are trace elements in coal. Nitrogen, to some extent, is the trace element, not really huge. But then there are a whole lot of other trace elements that are present: selenium, barium, beryllium. There's a whole lot of trace elements. So we'll come to that later on. So how do they partition between the gas phase and the solids phase? Solids phase means what is discharged at the bottom. That's really need to be known. Because at the end of the day, there is no point just building a gasification plant if you don't know what are you emitting. Because in that case, the EPA will not give you the permission to build it unless you back up with your calculation. And then the other important issue is cost reduction in air separation. To some extent, not to some extent, to a large extent, the cryogenic plants are still the technology of choice because they work, but cryogenic separation plants are very expensive. So there are a whole lot of other technologies being researched to a great extent. Membrane separation is one. And then of late, there is something also called chemical looping air separation. It's a fair bit of work that has been done in Australia by other universities, not Monash, and but it's still at its infancy, the development of a chemical looping based air separation. So the other R&D needs, the fact that all coals, and more so the high moisture lignites, need to be pre-dried before being used in gasification in all dry fed and train flow gasifiers. All types of gasifiers are likely to provide almost complete carbon conversion. The entrained flow gasifiers, all types of entrained flow gasifiers. So there is not really much of a need to do research on that aspect, except identifying the temperature at which you will get highest carbon conversion and temperature at which slags will form and flow. Ash content of high ash lignites need to be reduced to 10% or below before being accepted in entrained flow gasifiers by blending with either lower ash coals or possibly petroleum coke. Petroleum coke is used in entrained flow gasifiers, not a problem. Low ash or high ash lignites can be gasified in fluidized or transport reactor. Carbon conversion is likely to be limited to around 90% if fluidized transport reactors are used, maximum 90%. Friable lignites lose their carbon through elutriation of the fines. That's the biggest source of carbon loss. And for hard lignites, fluidized bed or transport gasifier temperatures may not be high enough for full carbon conversion. That's the view I form. And therefore, new or modified designs are necessary for full carbon conversion if fluidized or transport reactors are to be used for gasification. No, only in entrained flow gasification. In fluidized bed or transport reactors, you don't use too much of high ash is a problem, but low ash is not a problem for fluidized beds. Sorry? Fixed bed also. In that case, low ash is better. The problem is with the low ash, low diameter coils. because they generate the forms, they go this way, secondary point. And that really limits the carbon conversion. So the last bullet point I made is that if you want to get high carbon conversion at low free rate reactor, you have to have either unit or modified.
You mentioned untitled fluorescent gasifier that external combustion is used to do the complete combustion of the remaining charge
Are required to be used.
So is it in practice? Because how does that affect the energetics? Because if you again put the CO2 back into the as an accident medium, after reaching the energetics of the
It's not up until recently. It's not up until this. Up until about 10, 22, 23 periods, about 20 years ago, more than 20 years ago. It was not that. That was floated, and then all the focus shifted away from gasification because of high cost, and then that became valid. The point I tried to make there was that fluidized bed gasifiers, or for them, transport reactors, by definition, because they work at low temperatures to prevent agglomeration, limit the carbon conversion. So if you limit the carbon conversion, then your task is to have higher carbon conversion. That's one option, is to have a bound, either in an integrated combustor or an external combustor, and you go to do the CO2 tank. So that way you do the energy. And then, sorry?
I was curious to know that, like, apart from all these types, if polygeneration system is my purpose, which one would be the best?
The one which gives you the most reliable operation. So the most reliable is yes, flexible, but also gives you the consistent quality of the gas. Because for polygen means power as well as other products. That's why it is poly. So gen is from power, poly essentially goes from chemicals. So for chemicals production, depending on what the chemical is, you need to have a consistent quality of the gas. If it changes, then we need to have some gas quality changes, whatever we call it, some kind of shifting or some kind of other reactors in between. So, so from that point of view, I think the important aspect is to choose a gasifier for which a lot of experience is available, and that it gives consistent quality. Then the other point that I make is none of the country operating IGCC plants, so does not the Mississippi ones, were designed for lignites. For IGCC to be used for lignites, large-scale demonstration is required for all types of lignites. Fluidized bed or transport gasifiers may require separate combustors, if carbon from their discharge is to be utilized. And if the lignites have high alkali levels, and by high alkali level I mean 0.5 to 1% of most sodium content. Sodium is associated with chlorine, so that makes it more difficult. So that's the definition of high. Anything more than that is super high. That you then require the demonstration of quench gasifier. And that's precisely what the Siemens did. They had a quench system right in the middle of gasifier. Characterization of the solid wastes discharge from the gasifier. So one thing that you can do is the solid residues that you form in show up. You really to them again holistic picture. You should you shouldn't throw them away. You should analyze them and see the reachability so that
if these are dumped or disposed, is there any danger to groundwater because of what may leach out of these soils? That can be found. A combination of exopolisms, etc. If it is in a crystalline form, then it is leach in atmospheric temperature and ventilation. Unless it is treated with acid, which is never an issue. And then the other one is the development of a reliable system for feeding dry lignite to pressurized reservoir. That, in my view, is still an unresolved issue. The major generic need actually the gas separation, because for chemicals production from coal, it's because you are not generating just CO and hydrogen, but you are also generating a lot of pollutants. So gas cleanup is extremely important, and then again, it's very important is the separation of the gas. So for example, when you do the shift reaction, you are shifting the carbon monoxide gas using steam that you supply to more towards hydrogen than carbon dioxide. So you have to have a proper technology of the gas separation at those volumes, keeping in mind that there may be other gaseous trace species. So it's not that straightforward. So that's what I mean here. So that's a lot of work is going on the application of nanotechnology. So my final comments on this is that coal gasification power generation represents still a very small fraction of power generation compared to total coal-fired power generation capacity, which is currently, as I showed in the first lecture, 15 gigawatt electrical. All industry is a very conservative bunch of people, dominated mainly by mechanical engineers. The gasification plants are still specifically a chemical plant. So my first degree is in mechanical. I'm now in mechanical. I have a lot of things. But that's an issue. It's an issue. I mean, I have often faced.
Is it the perception or is it the
perception? It's a perception. How do you change the perception? Those who have been operating power stations for 20, 30 years, they will say, oh, that's chemical plant. That's different. Let's not go into it. It's only this small reactor and this tall. And ours is huge, this cross section as well as the 30 meters now. So you need a different set of skill set to explain to those people. Immediately, first thing they will throw you out. Particularly if you are young, as you get older, then they try to listen to you a little bit more carefully, but not necessarily that you will always absorb it. So, I mean, this is something that I tell the industry people when I give courses. That look, you have to have a mix of people amongst your employees. Otherwise, you will only get on this side of the story and not the other side. It's perception, nothing else. Petroleum plants, chemical plants have been working even before I was working. Power stations are over, so there's no reason why it cannot manage that. Choice among IGCC, air-based IGCC, oxygen-based IGCC, PC and CX, pulverized coal and CX. One issue that will become important is the way the new power plants are being selected now. Several proposals for IGC demonstrations are still in the pipeline. You will see them if you Google. However, the proponents of new power projects are not waiting for this to be genuinely available. In the meantime, the supercritical and anti-supercritical pulverized coal plants are becoming more and more widespread. this could then become so entrenched in the near future, and it has become entrenched, that IGCC without CCS may penetrate the market only when co-production of our chemicals can be economically demonstrated. Otherwise, a private company will tell, why should I do something which costs $5,000 per kilowatt when I can build something at $3,000 per kilowatt, which will give me a lot of power which I can sell 24 hours a day, something like that. So that's basically this particular module. If you have any question, otherwise I'll move to the next one.
So you said that the whole thing is arbitrary of the way so that we do
Or why it is.
Right. Why it is. Coal feeding is without gas solid presence of gas, just the solids, is easy to do in small scale using screw feeder. 10, 20, 30, 40, 100, not a problem. Kilograms per hour, not a problem. You can easily do it. You won't see the problems. But then, if you go to higher and higher levels, larger and larger flow levels, there is moisture inside even in the dried coal. At large volume of coal, the rheology becomes a big issue. Rheology is related to some extent to viscosity, but rheology is much more than viscosity. It's the friction or the interaction with the walls at large volume. Those forces become so dominating that you have to have some control of engineering. So it's the rheology issue rather than anything. It's not a problem that you will see in the laboratory gasifiers.
So what will happen is, say for example, you know how all these idols are made by before the pujas and all. They use clay. Clay is extremely hygroscopic, and that's how you can mold it, and then you can. So if you have coal, then also say you have some of the clay minerals inside the coal which you very present, or clay that is present supplied, or dolomite that is supplied extraneously to the capture and so on. The interaction between these two different kinds of materials, one being hygroscopic, the other one is a loose source of water, it changes the dynamics inside the feeding tube. So what happens, what you see, is that gradually the internal of the feeding tube, it will become lined with some of those materials, whether it is pure coal or coal and the other things. And to simply go around here to the cross section will diminish to such an extent that the feed rate will be interrupted significantly. So it's and that is nothing but what's that force called? Obviously it's not analysis, but it's the force of attraction between this material and in solids mechanics. There is a name particular for it. So that's the reason. So people have tried larger scales. So screw feeder won't work in that instance. To go there, yes, that's technically, yes, that's right.
The problem is, if you are doing for IGCC, not a problem. changing the gas composition and therefore changing the heating value is a non-issue, right? And but if you are using it for chemicals production and then all on a sudden periodically you are injecting steam, then the other things will be affected. Temperature will be affected, then the gas composition will be affected, and therefore that will not be a preferable option. And ideally, you won't be able to sell a technology to a client telling that, look, you have to, in addition to monitoring the gasifier and its status all the time, this is another piece of equipment that you also need to, so they will say, I'm not buying it. Flexibility, yeah. So it's 2 into 100% rather than, or 3 into 50%. Yeah, those sort of redundancies are often considered. Again, so those are options. Those are options. Compared to supercritical advanced.
Configuration. With power as well as something which you can sell and therefore can justify the high capex. As simple as that. That's an economic decision. It's not just technical, it's technical.
The CO2 capture can also be used for oil drilling. That can also IGCC from the level of IGCC only cannot be cover that.
You can, provided the gasification plant is close to where the EOR uses are. So at the end of the day, it all depends on the economics. So, for example, in Victoria, where I come from, the Japanese, they are considering, not considering, they are going ahead and reviewing all of their steps. They are planning to build a gasifier, do the shifting, generate hydrogen, separate the CO2, store the CO2 in Victoria, and ship the compress and cool the hydrogen and ship it to Japan. So, because in Japan the cost of electricity is so high, and Japan is actually a resource poor country, they import almost everything. So that's why they have a mix of everything in their energy generation, power production. Generation is not so it's all, if it is justified, anything can be done. Economically justified, anything will be done. At the end of the day, the cost of electricity goes up. That you and I are prepared to pay, and all sorts of super duper technologies will come out.
But sometimes efficiency also increases in IGCC.
So I say
Efficiency, in case of IGCC, efficiency also increases. So what are the main challenges in a country like India if you want to build IGCC?
main challenges is to know the gasification performance of high ash coal. Simple as that. And by gasification performance, I mean not only determining the temperature at which you have to carry the gasification reaction so that you can get highest possible carbon conversion, and then also determining whether that high ash is too high for use in flue gas rate, because then you will have too much of the ash to handle. Maybe tolerate, maybe manageable, or can it be done in rainfall gasifiers? Because it is a fact that the highest, the experience of gasification, coal gasification, at the highest possible scale, the largest possible scale,
is only available for in-train flow gasifiers, not for the other ones. And there is a reason for it. Sometimes when the projects fail, they never want to talk about it, why it may have failed. But if the project is successful, obviously they will, go high with the publicity, so that it can also be, talked about, hyped up by the politicians. They want to know only about success, not about failure. But the reasons for failure, unfortunately, in this world, are not shared.
But for the other side, absolutely, absolutely, absolutely. For higher score, there is none of the other technology also which must be attempted yet, I guess. Fluid ice bed technology has been attempted by DHL in 3G. They have a demo unit. 6.2 megawatt electrical scale, and back in 98, 99, a couple of engineers come and they are trained in CFD.
Does flow 3D, not CFX. But what is the current status of it, I do not know. Could be. But again, BHL is a monopoly. BHL is a monopoly in this country to some extent, even though the market is open to competition to others as well. So if anyone has the ability to take a technology forward, it is the companies who enjoy monopolistic competition. If you are living in an oligopolistic environment, why will they take risk and then not get anything out of it in the near term? If they don't get a market return on the near term, some people at the top level will be castigated. So there lies the thing. The same thing doesn't happen, for example, in China, because everything is told by the government, so they can take any risk that they want. Works, doesn't work? Okay, let's move on. So that's what it is, I think. So that's another point that good that you have raised it, is that we as scientists and engineers, we can do brilliant scientific work, okay, develop understanding, mechanistic understanding for everyone's benefit, for your own benefit, but never lose sight of the big picture. That at the end of the day, your engineers are working to make something, produce something, make it work in the near to intermediate term. Of course, there is a need for blue sky research over the longer term. That's indisputable. But for technology of this type of things, you really need to ask questions yourself, the hard questions. What if this happens? So what if type of questions. So never lose the big sight. Is it going to see the light of application in the near to intermediate term? Not obviously always you have to do that, because if you are doing a master's or a PhD, you are developing a sort of a skill set which can be applied across a range of disciplines. I mean, a range of allied disciplines, let me put it that way. Not that everyone has to work in order to build a 250 megawatt fluidized bed plant. That's not the thing. It's the development of the understanding, development of the skill set, development of the manpower going forward is extremely important. Otherwise, you will be importing the manpower from other countries, and then we will be twisted in your capacity to do anything. So this, in as much it is possible, it is important, but the longer term vision has to be kept in mind all the time. That what is the practical implication of my research? That has to be clearly articulated. Is it for the near-term development? Is it for scaling up? Is it for developing fundamental information which currently does not exist? And this is whether this is the novel way of looking at the problem. And that's what PhD is always, is the Doctor of Philosophy is the philosophical aspect, which is the most important thing. So you don't have to build a power station at the end of your thesis, but that's important.
They could not have hidden, they might not have hidden their reasons for success or failure.
But I think that was not a failure by any chance.
No, it's generated information previously that previously did not exist. Simple as that. You have to start somewhere. Then perhaps sit on it and then analyze and then go ahead with the next step. Not every program has to be.
So what is the next step?
There was some.
So next step is, okay, learning from what the difficulties were, what may have contributed to low carbon conversion, what may have contributed to low availability, why did it fail after X number of hours instead of going to 8,000 hours or long hours. These are some of the things. And then understanding the science behind those failures. And the point I have been trying to make in the last 4 days, is that now we have so much analytical and modern tools available, we can do anything that we learn within a very short period of time by assembling a group of people with complementary expertise. We need mechanical engineers, we need chemists. That's what we do. If you have a mathematician, we need a complementary. Okay, so here I'm just sharing as much as I can some of the so this is about the pilot plant operation. So this is the type of same type of code which we used for CFS. We were asked to use the same type of code also for testing investigations, the specialized high temperature fluid spread. And these three are the ones that we have that come from Victoria, and the other two other one which are from the year 1 code and the Lockyer codes from Australia. One is a very high sulfur code, the other one is the high sulfur, high sodium, high chlorine, and even for gasification purposes, 0.06 of 1% sodium is high. So there you have something which is 1% sodium. It is as if the coal has been soaked in salt for a few days. Then it becomes an issue. It will have to be reflected in the corrosion of the internal heating. At high temperature, reducing the alkalis and corrode, the metallurgist will tell you they can corrode it when the defected. And that has happened all the time. So this is the one that I was trying to mention, high sulfur in one code, and in one case is the calcium content was really, really high in the modular code. so much so that the transmission goes even its full brightness. This is something that we have already seen, as I mentioned before. If you take a certain amount of these poles, the 300 poles that you take, put it on a receiver and seal it, and then subject the fine samples to STM, when you see it right at the end, really plain structure, which I call UV structure. I will call UV structure. I mean, it's difficult to gasify within gasification environment at 900 degrees. So this also you have seen, so I will not go into it at all, you know. So there was these two that I will share my experience, these two pumps, and there is where we tested the three Victorian down poles and the high sulfur local pump. We did it at 1 bar and 10 bar, and 1 kg per hour to 300 kg per hour, and depending on the type of pole, we switched between 800 and 950 degrees Celsius. Remember that in a large gasifier, varying the temperature is not an easy task. In small scale you can do it, but in large scale it is very, very difficult. So our objective that was specified to us by the process that tell us what will happen if we gasify them in the air, or what will happen if we gasify them in oxygen enriched by, what is oxygen enriched here? By the iron. Air is 2377. Right? So oxygen enriched air is more than 23 oxygen and corresponding atoms. But keeping in mind that if you increase the oxygen content, enrich the air with oxygen concentration, then you will be essentially feeding more oxygen than the gasifier. Now the gasifier, when it was designed, it has a maximum cold feeding rate. We would like to operate it close to the maximum cold feeding rate in order to use it fully. But for that maximum cold feeding rate, you also have a maximum oxygen level that you can feed. Otherwise, everything will be carbon dioxide. So from that point on, when you have decided, okay, I will build a pilot plant gasifier, it will be 300 kilograms per hour. The corresponding to that 300 kilograms per hour for your pole, you know how much carbon is there, and that will then back calculate how much oxygen flow you will need. And that's only one side of the story. And the outside of the story is you also need certain gas velocity to operate if it is circulating fluid to stay within the velocity. So accordingly, if you have fixed the oxygen and you bring the other amount, the nitrogen by the other amount, get the right velocity to get the fluidization velocity in the range that you want to operate. So that's why it is oxygen enriched there. So not all rigs will be able to go to oxygen, full oxygen, even though the large scale rigs, that's what will happen. But in the smaller rigs, 10 kg per hour is also daily. So that's why it is.
So this is the fluidized bed gasifier. There's the one on the left side, and then this is the transport reactor gasifier. So let's look at the fluidized bed gasifier. The red bit is the main gasifier and the cyclone, the candle filter, etc., which are in there. And there we kept different levels of oxygen, oxygen-enriched air, and steam injection. Steam, as I said before, is also for controlling the temperature. And then also you provide steam at the top levels, because we were led to believe that these brown coals will generate lots of tar. So we kept the provision that we will have oxygen and steam at the top end, so as to break the tar, so that the candle filter after the cyclone doesn't see any tar at all. So eventually we did not see anything anyway, even without the application of steam at the freeboard. So this is the schematic of the rig. We did about 3 or 4 under atmospheric pressure, and then we straight away moved to that.
Oxygen we wanted to use for tar. How can you tap tar in this form? So what is thermal breaking? So that thermal breaking, the oxygen is just oxygen. If it doesn't react with something else, it doesn't use it anymore. So a little bit of the tar is consumed in the process with the fuel, so whether they will consume only the tar or some of the CO and hydrogen coming up is anybody's guess. No one knows. So that's why the permission was kept. And we will try all this. The luxury of trying all of these things in time. No. Steam, on the other hand, what it does is, steam actually breaks the bond, the high hydrocarbons, long chain hydrocarbons, from a different mechanism.
Completely by a different mechanism. It's not thermal breakdown at all. We will be supplying the steam only, in this case, we are supplying it about 10 bar. So what's the pressure, temperature at 10 bar? Just with this superheat and all, about 200 degrees, close to that. So it's not thermal heating that's causing it. It is the breaking of the bonds by steam through a different mechanism. I cannot recall exactly what it is now, but that's how it is. But it is a well-known fact from small-scale scientific work. So it was developed in the laboratories. This is what can also happen. And this is what is applied in practice. So again, there is a use of research over there. Then, okay. So this is the, just to get a hold of the figure, this scale, impression of the scale. The gasifier is within this structure. Then you have the steam generator. Then you have the incinerator. We were actually burning the gas off day in, day out. The gas is eminently combustible. And then this is the lock hopper, which is not seen in here. It's on the other side of the gasifier, but this is how the lock hoppers look like. This is the top lock hopper, and then which goes at atmospheric pressure, and then underneath there is the other one, which is at the reactor pressure. So the 2 lock hoppers in tandem, they cycle between here, this vessel. Eh?
Yes. So because it is not seen here, so that's why I'm showing you. Oh yes, okay. Sorry. See, good. So this is the lock hopper. And when I say that
3 different layers of steam injection, you have to have this oxygen and steam injection tuyers surrounding the main gasifier, right? So this is how it looks like. Now, this is, and then you have all the other auxiliaries. This is the main hopper where coal is fed first, and then it is transported through a conveyor belt into the top of the lock hopper. That lock hopper is kept ready all the time, the top one at atmospheric pressure, and while the bottom lock hopper falls below a certain level, then you stop the bottom lock hopper for a few seconds and completely download the coal from the front top lock hopper. It works very well, but the problem is if coal is moist than usual for whatever reasons can be, hasn't been dried properly, hasn't been uniformly dried, or has reabsorbed moisture. So all of these things, then they will breach the lock hopper. They will block the lock hopper. So in the large plants, there are other engineering issues which can be, which has, even though it has viscosity roots, but then the problem can be examined and simulated in the laboratory to see what sort of bridging is occurring, at what depth it is occurring. Remember that the top lock hopper where you have coal, and then that coal, when it is closed, it gets quite compressed. So by the time you open the valve, automatically though, you will see from the pressure transducers in the bottom lock hopper that nothing is flowing. So what you do is you pick up your walkie-talkie and tell the workers in the in the ground over there, go and bang the lock hoppers with the bottom. So these lock hoppers, I haven't captured it, but they have a lot of banging sign over there. Problems become a lot less if these are big. These are scale effects. Wall effects become more, problematic in small scale. But in any case, there is the pilot plant trials are very, very important in the sense that you not only get a chance to test your scientific assumptions, but also identify what are the other engineering issues that will be faced by the operators. So the whole purpose is that. And then hopefully bring it out in the open. And that's the reason I'm telling this to everyone. The problem is not everyone wants to know the bad things. Everyone wants to know the good things. Okay. But we, of course, we did not do it just suck and see approach. What we did was we built a one-to-one model, absolutely one-to-one model. Okay, so we had the riser here, the big one, then the cyclone, and the return deck exactly where it is. Eh? No, it's not there. Sorry? Actually, no, it's pressurized. Yeah, but at least you will know the hydrodynamics of it, because pressurizing a perspex model is very, very difficult. Yes, you are right. So, so you can see this photograph was taken when it was fluidized. So it had the expanded freeboard, and these two are the gas injection ports at the top ends, and then you had a lot of these things at the bottom, and a whole lot of transducers here and there, so that you can measure the gas composition, sorry, not the gas composition, the pressure drops, and you can do the actual circulation balance, that are you going to get good fluidization under ambient conditions, so that it will be not only it will be fluidizing, which is important for gasification. Gas solid contact is how it is, and then more importantly, you will also know whether there is any channeling of the particles or not. So one-to-one cold model is extremely important. Now the question is also in one-to-one, what will be your material that you will be testing with? Just imagine if you do it with coal, you won't see anything, right? Because the surface will be all be covered with this thing. So it's very important to use a material which hopefully has density similar to the density of coal. Unfortunately, there are a whole lot of materials which are available like that. Biomass sawdust, for example, is one such. So nature has given us one less problem to solve. So anyway, so that's how we decided that we will do it this way. That's how we decided that we will inject, we will position the turrets at this level or that level, so as to assist the circulation. Because remember, maintaining the circulation is the first and foremost important thing. Without that, gasification cannot occur. And then we also can see whether there is any bridging happening at the bottom of the gasifier, bottom of the reactor or not, bottom of the riser or not. If there is any bridging, then obviously that will also most possibly be replicated in the big rig. So one-to-one scale development is very important. The hot one, yeah. So hot one. Now, so what do we do is the same principle as in the PF combustor. We have a gas-fired burner. We put in hot gas, because inside the gasifier you have plentiful of refractories, and that refractory is a heat sink. So that temperature has to come up. So what we do is, at atmospheric pressure, we start feeding in gas. When we see that the temperature has gradually increased 100 or 150 degrees, then we start to pressurize about 100 to 150. So then we start to pressurize by bringing in nitrogen. We won't bring in air at all. Nitrogen, and then gradually we raise it to 10 bar. During that process, the temperature will also slowly increase after a dip, initial dip. And then once it has reached the temperature above the ignition point of coal, and we discussed that on day one, then you start feeding in coal. Not fully, not at full load. Sorry. Yeah. Coal feed was closed. Coal feed was closed. Correct. Now, because the exhaust line has to be open.
And remember that right at the top, which I haven't shown here, there is also an explosion vent. So explosion vents, do you know what explosion vent is? So what we'll do is the design of the explosion vents is highly specialized. There are two layers of metallic strips. The thickness of it is very, very important. So it senses the pressure, and then when the pressure there is gone above a certain value, remember that the allowed the design pressure is always 1.5 times the operating pressure. That's more or less a core requirement whichever country in the reactor. So your explosion vents are put slightly closer to that pressure. So that if for some reason there is a pressure drop, there is a pressure buildup because of this reason. Then some line has clogged, then it will open. It's not a pleasant scene though, because then you're releasing everything out in the open, and then you have to report, you have to front the inquiry, and then why it happened for good reasons. There's a loss of time. So it's better not to have it, but then that experience can also be be had from this type of thing. We experienced it once. Okay. No, initially there is no bed material. We did not use in gasification any bed material. Hot gas. The purpose of depends on see, you are looking at only about 350 to 400 degrees centigrade. The ignition point is that much. After that, as soon as there is oxygen, for ignition you need two things. One is the temperature and the other one is the oxygen. So if temperature is already reached, and then if you are supplying oxygen, as soon as you feed the coal, it will push, it will step. So this one needed about 6-7 hours to start. Now that point, yeah, that's right. That's right. We did it very, very slowly. We did not want to take any risk because, and just because it was first of its kind, so we did not know anything about this sort of things. So best is to play safe, and even if it takes one full shift for cold startup. There is also something called hot startup, which means the plant is the gasifier or the reactor is hot, the cold feed is not flowing. So that's hot start. That's very, very good. That happens all the time in the coal-fired power stations. The nighttime when load decreases, they decrease the coal feed rate, but then they increase it very quickly. So load following capacity of these units is great. And this is no exception. Great. Okay.
How did you heat the gas?
How do you heat the gas? We burn natural gas.
Burn naturally. And then you mix it with the
Nothing. For heating up, you need to send it just on its own, because it's all the factory line inside.
You gradually increase the same supply.
Not really, we did not do that here. We just bought a certain I can't recall what the way it was playing. It might be about 8 or 10 kilometers more than that. Best to not to temper it. Just send the whole temperature, and by the time from the burner to the gasifier to the line to make it insulated, so that we have to apply a temperature drop. It's quite significant. So it will go into the gasifier interval such a level, such a money level.
So after making physically the bed material will be.
We guys can gasifier, no bed material. Why do we do it? There is the ash element. I mean, people have tried to use bed materials sand. Important. Gasifier not important.
because gasifier predominantly, gasifier everything is balanced. The exothermic reaction is completely balanced by the endothermic reactions. In combustor that doesn't happen. So the heat has to be removed by something else, and that's one of the roles of bed material in combustors.
Even steam was introduced much later when it has reached the temperature. So I will show you a graph.
Take to reach. True. A char, because as I said, coal gets pyrolyzed very quickly. Small or large, in the less than a second range, more or less. Condition, and the pressure is also atmospheric. Cold models are almost always like that, so that you can actually see it. Otherwise, you will have to make it high pressure. You'll be looking at other kinds of material which may not allow you to actually see what's happening. Okay. That's the biomass that is circulating. So this is the hardwood biomass. There are all types of biomass available: softwood biomass, hardwood biomass, etc. The hardwood biomass, the sawdust from it, the density is closer to that of coal and char.
Gasifier, the gas will be hot, so the temperature effects will be matching with that case. So how the hydrodynamics might also change in that case.
Hydrodynamics will change considerably, absolutely. So the way it is tackled is that, first of all, this allows you to see what's happening, whether there will be any massive problems or not. This allows you to determine how much gas you will be feeding at the bottom for fluidizing, how much gas you will be feeding at the top, how much even higher positions, in order to see the circulation around the whole loop. Otherwise, that will be very difficult to do in the hot field. You want to do the trial and error. So this gives you a very good first level indication of what should be the gas flow rates,
what should be the distribution of it, and at what intervals you should be injecting the air so that it circulates. So that's the only information. Now, what then happens is, as you rightly said, the temperature will be different, a lot higher in the large rig. If you can use this data, put it in the CFD model, then you have developed a framework to match this. Then you use the model to predict the same thing, but at higher temperature. Get an indication as to what the flow behavior, what the thermodynamics, what the temperatures, etc. will be like. Even though you are not able to validate that until such time you have done some actual hot measurements, and even for the hot measurements, in majority of the cases, the only hot measurement that you will be able to do is the carbon conversion at the end of the reactor and the gas composition. The other ones, of course, you can also match or validate the model for gas temperatures, because in the hot rig you will have thermocouples at different levels. So it's a combination of the two: cold model experiment, develop a model, use it for higher conditions, then validate it even if it is part, in part, and then go forward. Okay. So, okay, so what's in here? Okay, so the trials that we did, I was asked to check the effects of this 3 Victorian brown coals, first 3, and the South Australian coals, and because it was a collaborative work, so the US Department of Energy sent 2 of their lignites, and correspondingly we sent our lignites to test in their transport reactor, and that's when I spent time over there in 2 states. So we looked at the effect of bed temperature and bed height. We looked at gas composition, including the composition of ammonia, hydrogen cyanide, and sulfur compounds. Carbon conversion, we looked at the effects of steam addition, what that does to the temperatures, what that does to the composition of the gas. And we ran it at oxygen-enriched airborne and air-blown mode. We also looked at the characteristics of the bed char and the filter fines. And we did all the analysis that we were talking about 2 days ago, electron microscopy based, X-ray diffraction, thermomechanical analysis, etc., to make the overall holistic assessment. So thermomechanical analysis is this. So it's a rig where you put, this is the one that with which we determine the ash character. So you put the ash there, certain height of it, heat it from this side, so that's thermo. Then you put a load on it, a designated load, and as the temperature increases, the ash will soften, and the piston with the load will go down, and its movement is to the micron level, will be detected, measured by transducers. Okay. So, and you can actually literally see the peaks and the troughs. So thermomechanical analysis does tell you where, at what temperature the ash character is changing. So if it can be done right at the beginning, then you can literally see at what temperatures you need to avoid. Okay. So this is a typical process data. The bottommost curve is methane, and because methane comes directly from pyrolysis, so that's why after a while it stabilizes. Then the second one, the black thing with hydrogen concentration next to the yellow bits, and the yellow bits are CO. So it's predominantly CO and hydrogen are 1 to 1 in this instance of that coal at that temperature. So technically, you can use that for a production process of chemicals which requires 1 to 1. If not, then you need to shift it. Anyway, let's not go into this now. Then the upper one is the total combustibles, which is CO, CH2, CO, hydrogen, and CH4 in our instance. This one, I mean, this one. Then this is the average bed temperature. So what we had was, I can't recall now, about 8 or 10 different thermocouples at different levels, at different diametrical locations, and then and those are simultaneously they are measuring, and you can put that all in the same control software, which will give you the screen, on the screen directly, the average bed temperature. So, it is a very good indication of the health of the bed, because if it swings heavily, the bed temperature, average bed temperature, it means that some of the problems are either happening or have happened. Apart from that, of course, you have small screens of the individual temperatures, so that you can also know whether this problem is limited to a particular region, limited to a particular level, or this is widespread across the entire bed over the entire height. And then the topmost is what is that? Average freeboard temperature. So, average freeboard temperature, because we were injecting some steam and there was some excess oxygen maybe coming in. So, average freeboard temperature was higher than the average bed temperature. And then the pink one, and then oh no, sorry, I told you wrong. Sorry. In this case, no. This is the average bed temperature. This is the average bed temperature. This is the average bed temperature, and this is the average freeboard temperature. And this is the total steam flow to the system. So, that is quite interesting. So, in our case, we were, at least in that particular run, we are able to maintain the bed temperature and the freeboard temperature more or less same. So, it was more or less an isothermal reactor. But you can see proportionately how much steam we were using, a combination of steam added to the different layers, different levels. Because it is a fluidized bed, temperature has to be controlled, so steam has to be supplied a lot. Otherwise, temperature will run away, bed temperature may become very, very high, and then there will be a problem. So, so this is just one set of data, process data from one particular run. I think this was a short run. So 1748 we stopped, and we started it about 10:48, so 7 hours. So what is the final results though? The final results are that we could not get more than 87% carbon conversion for our coal. For South Australian lignite, it was about 83 maximum, but the lower one, a lot of the times was a lot lower. And the higher carbon conversion was achieved within that range with coarse sulfate and stroke or bequated coal, and that is the reason why I say the friability of the coal, softness of the coal is so much important. Because if it is friable, the coal will go inside, it will disintegrate into fines for attrition between the particles, among the particles, as well as thermal fragmentation. So, if they attrite and you have designed your fluid bed for operation for a particular size and accordingly the velocity, etc. So, these fines will then illiterate away without getting a chance to get converted. So, that is the reason. So, we found out that the factors affecting conversion, carbon conversion is coal type, concentration of fines in the feed coal, illustration of the fines originally present in the coal as well as fines generated from the coals. Of course, they are also affected, the carbon conversion is also affected by coal feed rate and reactant concentration, pressure and temperature. And then bed drainage, bed level control, which is a must for fluidized bed gasifier. I will come to that. Recirculation of the fines that will dictate the cyclone efficiency, pulsing and purge in the recirculation leg. And lowish coals, my view is that carbon conversion is limited by illustration. Let me go one step back. Here in the recirculation leg, we also had nitrogen pulse. Why it is? Because this is the standard fluid flow, solids flow in any pipes. You have to allow the solids to build up, and the solids build up, the extent of solids build up is indicated by the pressure transducers, the value of the pressure transducers. Of course, the more build up there is, the bottom ones will be showing higher values. So then if you allow it to build up, then obviously nothing will flow. So, so you'll have to make it flow. That's why you need the recirculation leg. And that's a big variable. And that's something, that's why I wrote it in here, that the recirculation, purge in the recirculation leg. Because it can determine so many things during the operation. If you are not purging it at the right level, then the bed level will change, and by bed drainage, now let me come to that. Over a period of time, the bed at any point of time is composed of three things, three types of materials. One is the incoming coal. The other one is the incoming coal, which gets pyrolyzed quite quickly anyway. Then other one is, it is the gradually converted char. And then other one is the ash, in which almost all the carbon is gone. Not 100%, all the carbon is gone. So three different types of materials. Their densities are very different. So the char's density is about 0.8. And then as the char loses more and more carbon, eventually the ash density is about, if it is predominantly silica, then 2.5, the specific weight of it, specific gravity of it. So there you have a variety of materials of varying density inside the bed. And you would ideally like to keep a consistent quality of the bed material. So what you do, you take out some of the drain materials through the drainage. So there is a lock hopper, because it's pressurized, and then there is a screw feeder. So every now and then, and that can be determined by the pressure transducers put on the lock hoppers. When it sends a certain signal, it means it is full. Then you close the top valve of it, so nothing can come from the gasifier, and then you open the bottom valve through the screw hopper, you discharge the bed material. So bed drainage is also very important. The reason is that if you do it too frequently, then you will, in all probability, you will also be preferentially separating one type over the other. So how frequently you drain it, that has to be established. It is known to the manufacturers, those used to do, but our task was to develop this information, give it to the power generating companies so that they can make a decision. So that's why we found it. So, but I wouldn't say that I am the first person in the world to identify this. Most possibly, I am the first person in the world to report this. Because not everyone wants to share everything for some reasons. So the other key results, fines generated from the attrition stroke reaction is about 6 to 8% of the coal feed. So there are fines together with the coal going into it. There are fines which are generated as a result of the attrition and the reaction. So, which we found by sieving the coal, the material that comes out from the cyclone eventually, that that it is about 6 to 8% of the coal feed is the fines that are generated. And those are the ones which are completely going out of the system, and they are basically they are 95% carbon. So, it is a substantial carbon loss that happens because of the friable nature. Then what we did was, okay, it's a substantial one, then how can we utilize it? So, we did it in a small laboratory combustor in a PF environment, a down feed PF furnace, and then we found out that within 3 to 4 seconds, 1100 to 1250 degrees Celsius, 20% excess air, we can easily convert everything, burn everything away. Maybe that will be fed into the to the designers. I don't know what happened eventually. The burnout, the carbon burnout from the combustion test were well in excess of 99%. And only 5 to 20% of the original water-soluble form of the alkaline metals were present in the fines. That's actually quite important, because if you are utilizing the fines by combusting it, remember that fine is not only rich in carbon, that fine may be also rich in the alkali metals, because the alkalis get evaporated, but then they get settled onto the surface of the fines, which have very high specific surface area in the cooler zone. So, it may actually be over a longer term, it may be a problem burning it off, because those will give rise to so much fouling. Particularly the CFBC work when I reported 2 days ago, you can see the fouling on the air-cooled probe. That's how it will happen. So, it needs to be investigated, and we obviously did not investigate it to through any longer term test. And then we looked also at the char morphology, some of the char which stayed inside the bed. We found that some of the chars are porous inside, as shown by the left hand side SEM, I mean the micrograph, but some of the chars are absolutely covered by the fused minerals covering its surface. Therefore, it will not be accessible to the reactants. Steam and others, carbon dioxide or oxygen, will not be able to penetrate that layer. So, these are some of the important information that you can actually generate. So, the key information that we also generated, the first bullet point I happily report to everyone, the no tar observed during steady state measurement point, and that always raised a few eyebrows, but fact is fact. At least the way we operated, tar was a non-issue, but up until that time, everyone talked about Victorian tar, Victorian brown coal at low temperature gasification, tar would be a problem. It was not a problem. And I'm talking about the 100-hour tests. It's not a problem. The gas composition, air-blown mode, this is the composition that we got. 2.7 to 4.1 megajoules per kilogram. So, it is somewhat combustible. Up to 1600 ppm of ammonia, up to 100 ppm of HCN, and up to 100 ppm of COS. So, these are quite high value. So, you really need to have certain other means to bring them down. The sulfur without dolomite, only the high sulfur coal had about 3000 ppm of sulfur, hydrogen sulfide, but with dolomite fed separately, it could be brought below 50 ppm most of the time, around 10 ppm mark. No detectable sulfides during the Victorian lignite-based tests. We did not see anything. And use of the dolomite also reduced the ammonia level by about 50%. So dolomite is actually known to be a ammonia cracking agent. Dolomite as well as limestone. Dolomite is roughly, depending on where you get it, 60% calcium carbonate, 40% magnesium carbonate. And the oxygen enriched air blown, you got higher hydrogen and CO concentration. Methane concentration is 1 to 4%, and only tiny amount of other higher order hydrocarbons, and 10 to 18% water vapor. And the calorific value obviously was higher. And at higher levels up to 1800 ppm ammonia than air blown mode. And that's one of the problems with the oxygen blown gasification, that you may actually be seeing the higher levels of ammonia, because for some reason the ammonia doesn't crack under oxygen blown conditions. I forgot what it is. With dolomite it reduced by, but with dolomite we did not test for the Victorian brown coals. Dolomite we tested as a means for controlling the sulfur emission. Ammonia is also reduced when you use the ammonia at oxygen blown condition, but still it will be high. 800-900 ppm of ammonia is a very high value. And if the coal nitrogen is high, for example biomass, then you are most likely to get a lot of ammonia. So majority of the alkali in the char or in the filter fines. So we did not detect much at all in the gas, because there was a good condensing available on the char particles which were circulating through. And then assessment of the agglomerates. We looked at some of the agglomerates that we found at the bottom of the gasifier after certain rounds. I think this all came from the high sulfur coal, which gave us tremendous problems, not from the Victorian brown coals. So we looked at, so the first one in here is one agglomerate. This is one agglomerate that we looked at. So we looked at as to why it happened. So we mounted one agglomerate, and then with some of the spaces we looked into more detail, and then this area we looked into more detail here, and this area we looked into more detail here, and then this area, for example, we looked into more detail here. So what we can see in here is that when you see the presence of spheres, it means that it has gone to a very high temperature. So for some reason, the agglomerates were experiencing very, very high temperature, maybe due to the bed problems. Bed temperature was not high, or maybe the oxygen introduction into the bed was not uniform. Maybe it's both. So at least this type of electron microscopy based investigation can tell you precisely what may have happened, and therefore how you could avoid that problem. That okay, if temperature is being the problem, then you have to have the mitigation strategies to see the temperatures, whether you can reduce it or not. And then you can do the X-ray mapping, which we did plentiful, because it's quite exciting to do that. So here, each map is for individual elements, so you can interrogate it. So the top one on the left hand side is sodium, the one below is for calcium, the one below is magnesium, the one below is iron, and then on the other side is silicon and others. So, when on the scale of color means the concentration. So, if it is on the higher red scale, then it is more of it present in the same place. If not, so just to give you an example of this, if you compare these two, this is a highly, it is a silica rich particle, but here there is absolutely no sodium in it. This is, so one particle, it's just like that. But otherwise, almost everywhere you had a mix of sodium and silicon, or you had a mix of, in some places also you had magnesium like in here, but chlorine is specifically we were interested in finding, but we did not find anything much in the agglomerates, which means chlorine had gone into the gas phase, which that's what you would expect. So, the X-ray mappings are a fantastic tool to identify what is present and in conjunction with what, even though it will not tell you what actually the composition of it. For that, you have to grind up the whole thing and then do X-ray diffraction, and hopefully if there are crystalline compounds, then they will give you, or you can interrogate each and every point there to get the point-wise composition, and which is a EDX. So, similarly we did the other one. So, these are two just examples that I am giving. And then we also subjected some of these deposits to ash analysis, and the results were very varying, very varying. It tells us that in some cases, in some of the agglomerates were not all were very reasonably stable beyond this temperature zone. Between this it is fine, and above this also it is fine. Some were beyond this it is fine, some were it is not fine anywhere except here and here. So what it tells is that the temperature the ash character can be quite at least for these coals quite unpredictable. But one thing is true, that in the higher temperature range it can become quite stable, and because it also melts, then then removing it from the gasifier will not be a challenge at all. So that's why we said what we said, that that Untitled Gasifier is one way to go. But let's not go into that. Then we did the X-ray diffraction as well, and which does tell us what are the predominant species. It is an important complementary expertise to know what exactly are the crystalline compounds, but on their own they do not serve much of a purpose. But this is what they get. Bed drainage. No, it will be should be lesser size than your outlet size. Otherwise, it will not be fine. And then you have to have purge there as well in order to dislodge if the solids have unpredictably deposited there. So it's just like stones. It's they are randomly falling down. If they fall down in a structured manner, then obviously it will be easy. But if they fall down in an unstructured manner, then it will be typical. So the important thing is knowing what intervals you will be draining the bed, and what else you need to provide to drain the bed, that's also important.
Fluidized beds have different variants. This is the variant of pressurized high temperature inclines, which means this does not have any extension at all. So the idea is that the gas jet that goes underneath, that will create a sufficient velocity and flow distribution, which will keep everything fluidized very nicely. Because if you have distributors, then there is a potential that this can clog the distributors.
And then you will have to no other way but to stop the reactor and then cool it down and then take it out next day. So HTW gasifiers, for simplicity's sake, that's the patent, no distributor. And the char agglomerates also we looked at this, and both by morphology and on the right hand side by the EDX, and it tells you that in some cases they are fused on the surface, but you can also get a composition of those ones. So these are very useful tool, particularly scanning electron microscopy. And these days it has become quite cheaper and quite easier to do it. Now you need only a table of 3/4 of that size to mount a scanning electron microscope. And with quota and everything, you may need a little bit more space, but that's it. And then we also looked at some of this, and I have shown here some of the beautiful micrographs. And what it shows is the so-called, this is a char agglomerates, the so-called woody character that I was talking about at the beginning. Those woody ones, or polished ones, or however you call it, which will be difficult under the fluid bed condition to convert, and that's clearly evident from heat. So this is directly in here. They will not convert by normal means. Okay, so the woody. Yeah. So this one was at the North Dakota facility, and similar temperature to pressurized fluidized bed, but similar pressure also, 10 bar. And the composition was, carbon conversion was very similar. For the Victorian brown coal, for the Lochiel coal, we had tremendous problems. The carbon conversion was even lower. And low values were too much fines, due to too much fines generated, and also the problems that we experience in the cyclones operation. Because the too much fines, cyclones do not like a wide size distribution. You cannot design a cyclone for that. You have to design it for a narrow size distribution. If you tell that you will be designing it for 2 micron through to 100 micron, it will be difficult. But that's what happens. Sometimes some of the coal particles go in, sometimes half converted char go in that are high, and then on the other extreme you have the fine ash particles. Anyway, the dry gas composition was what we showed, and the CO2 enriched air blown is that. And for the Lochiel coal, which is the high sulfur coals from South Australia, this is the value that we got. because it had high ash, high sulfur, and it was not as reactive and as the Victorian brown coal. And then, so the bottom line is, for both of these gasifiers, which operate at similar temperatures, but with different designs, the bottom line is carbon conversion is low, fine stroke friable coal not tolerated, declining reactivity with carbon conversion becomes an issue, external combustor may be required for complete carbon conversion, agglomeration is a major issue over a longer term, lower temperature may avoid it, but lower temperature will give you even lower carbon conversion. And of course, it will also affect the gas composition, the lower temperature. So that's the second last, and this is the last. So then we formed the idea that, okay, if these are the problems, gas composition is okay, carbon conversion is somewhat low, then what do? We suggested that we investigate entrained flow gasification, because there fine particles are an advantage, but there may be other issues. And what are the other issues? Other issues is slag viscosity. Low ash content poses a unique problem. Coal composition and reactivity, much more important than in combustion, but lesser of a problem than in fluidized bed gasification, because fluidized bed gasifiers operate at low temperature, so reactivity is very important. Entrained flow gasifier operate at very high temperature, so most likely the reactivity will be lesser of an issue. So that's the problem that for you will conclusion that we raise is generated, and the trace element partitioning between the gas and solids discharge for some coals and in particular lignars, that may be an issue. So these are some. So I then left to work for Anglo Coal and then to the IEA. And then when I came back to research work again, slowly after, then I convinced the Mitsubishi and others to fund entrained flow gasification work, and that's another story. So that's another part of the presentation. So I think, let me see if I can go to the next one or not. Quite large. So I think I would be much better off. Tomorrow is Friday, isn't it? So we have the entire second half. Okay. So I think it would be much better off to do it on Friday. What we will do is, having concluded that entrained flow gasifiers should be looked at, what we experienced, what we found out, how we did it, what we found out, what are the issues still remains to be here, and then I will talk about the ash viscosity research that I did. So those three things that I have, if I can cover tomorrow, then I will be back on track despite missing yesterday.